下面我们欢迎我们 Andy 我们的资深首席工程师来给我们分享 PMDK 的主题演讲。Welcome.
So I'm Andy Rudolph. I'm an architect in the data center group, and that's important that it's the data center group because that's where persistent memory first showed up on the Intel products. But everything that I talk about has been designed, everything in this entire talk has been designed for persistent memory on any platform. So when persistent memory shows up on client platforms, when it shows up on laptops, when it shows up anywhere other than these server CPUs, everything that I talk about here will still apply, including the standards, the programming model, the libraries, because we knew that we only had one chance. Right? We have one chance to tell people how to program persistent memory. It can't be you program persistent memory one way on servers and another way on client. And it can't be you program one way on Linux and another way on Windows. And it can't be one way for Intel and another way for ARM, another way for Power. So you'll see when I get into my slides, a lot of what I'm talking about is not specific to Intel. And that's actually a very important point, right? We think that it has to be a broad ecosystem for programming persistent memory, or it doesn't work. It has to apply to everything. Okay, so I'm going to talk a little bit about why we did PMDK. I'm going to give you some history. I'll give you the current state, and just like Jim did for SPDK, I'll talk about where it's going. So this whole thing for me started about 7 years ago. And about 7 years ago, we heard persistent memory is coming. And in fact, there were these products that were little DRAM DIMMs that had flash chips on them. I drew a picture of it over here. So these things are still shipping today. You can buy these from different companies. They have DRAM on them, and when they lose power, they take the contents of the DRAM and they put it in a little flash chip. And then when the power comes back, the contents comes back. So this is persistent memory. It's been out there for many years, and you can buy these things today. They're small by today's standards, 16 gigs. I think you can buy 32 gigs now, but they're very small and they're expensive. But they are persistent memory. Now, initially, these things were all, they were very new. People weren't quite sure how to program in them. So these things, all the access was actually done through a driver. And you just treated it like a little disk or a little block device. So there wasn't any new programming model. There wasn't anything like that to worry about because it was just a tiny disk. So did it really matter that it was on the DRAM bus? Well, for latency it mattered. For performance it mattered, but it didn't really matter as far as programming. You just used storage APIs. These things were later called NVDIMM-N by the standards bodies. So everything that I talk about applies to NVDIMM-N. But of course, for Intel, what happened then is we started shipping this Optane media, the thing I drew a little cartoon of over there. And the Optane media is much larger. We have DIMMs that are 128 gigs, 256 gigs, or 512 gigs. So now we're talking about systems that are going to have 6 terabytes of persistent memory in them. So now we're much more motivated to come up with a common programming model. So back when this was happening, we started looking at what should the first steps be for making a programming model. Now, if you've ever looked at persistent memory at all, if you've looked at any of the materials that we have online, you've seen this diagram, right? And this is the programming model for persistent memory. So this is the basic idea of how do I expose persistent memory through the operating system up to applications, right? And in this diagram, we show the persistent memory, but we also show these green blobs here. These are the things you have to add to an operating system. This is not a Linux diagram. This is not a Windows diagram. This is the common ecosystem programming model, right? It's meant to apply to everybody. Now, it has applied to a lot of people, and this is shipping today on Linux and on Windows and on some other operating systems too. So we've actually been very successful there. And the reason we were successful is we took this common desire to expose persistent memory, and we formed a standard working group in something called SNIA, the Storage Networking Industry Association. And this was now, I think we formed SNIA about a little more than 5 years ago now, and it was instantly very popular. Microsoft was there on the first day. Red Hat was there on the first day. A lot of hardware vendors were there, and a lot of ISVs were there. We have over 50 companies now attending, and we still have weekly meetings. It actually is still a very active working group. So you can see how much interest there was in persistent memory. Some of the things we had to solve here are, well, if you put persistent memory in the system, how do you attach a name to the persistence? How do you attach a name to your data structure so that you can be attached to it the next time the program runs? How do you put permissions associated with it so that people are only allowed to get to information that they have permission for? How do you back it up? This is just sort of practical. You can't just come up with a new API. It really has to solve these practical problems. We found that there were some less technical goals. For example, you really want to protect the ISVs, right? The ISVs, the software vendors, these are the guys who have to decide to spend time, to spend resources converting their program for persistent memory. So if they have to convert their program once for Intel persistent memory, and then somebody else comes out with it, some other vendor, and they have to convert their program again, then we have failed, right? It has to be done once. It has to be a common model. So as an Intel employee, this is actually kind of an interesting job for me, because I wanted to make a library, but it was not the Intel persistent memory developer kit, because I can't lock people into one vendor. So if you go to our website, the PMDK website, where the library is, you won't see any Intel logos, right? It's a common library for everybody. So to give you a little bit of the history of how we got here, so back in June 2012 is when we formed that standards body to come up with a programming model. We had a very large participation immediately, like I said. By January 2013, we saw enough interest that we held the first of a series of conferences that happen every year now, called the Persistent Memory Summit. Back then we started it out calling it the NDM Summit, but we decided persistent memory is the term we wanted to stick with. So every year in January, there's a Persistent Memory Summit. All of the talks at the Persistent Memory Summit are videos, made into videos and published on the web, so you can watch them. By July 2013, we started our first kind of early versions of code to help people program with persistent memory. And it was really just some ideas. It's still out there on GitHub. The repository is called Linux Examples, and it was just some examples of how persistent memory might be used. There's nothing there that you can use today and have to do anything interesting, but it was the beginnings of PMDK. And then by January of 2014, this SNIA twig that we started, the technical work group, published 1.0, the first version of the programming model that the operating systems were going to implement. Great, so we had a SNIA model. The SNIA model tells you how to run a program and how to open up some persistent memory and how to map it into your program. So you can now, with just a couple of lines of code, you can open up some persistent memory, call mmap, and you have a pointer in your program to 6 terabytes. So that's not very friendly to a programmer. To say to a programmer, okay, here's 6 terabytes, have fun. Immediately you start thinking, well, what do I do with 6 terabytes of persistent memory? I have a pointer to 6 terabytes. How do I decide what data structures live where? How do I decide which memory has been allocated and which memory is still free? Okay, and how do I make changes to it in a way that's consistent across crashes and reboots? So we went around and we said, okay, this is very raw, but how can we make persistent memory programming easier? And of course, what I did was I started going to customers. I went to ISVs, I visited dozens of ISVs, and I started gathering requirements. So every feature that's in PMDK today is something that came up during a requirements gathering, or suggested by somebody who wanted to use persistent memory. These are the top things that came up immediately. We need a way to track allocations. Programmers, you know, if you're taught C in college, you're taught to use malloc and free. If you're taught C++, you know about, you use new instead of malloc, but it's the same idea, you allocate something, right? There's always some way in the language to do dynamic memory allocation. It might be handled by the language, it might be handled explicitly, but you need some way to do that for persistent memory as well. The second requirement we heard over and over again was the way to do transactional updates. If I'm in the middle of modifying a data structure in memory, like a hash table or something, if I'm in the middle of changing that data structure in normal memory and my program crashes, it doesn't matter because memory is free, it's given back to the system, it's gone. Memory is volatile. There's no expectation that that data structure is there when the program restarts. But this is persistent memory. So when the program restarts, your data structure is right where you left it. It's in the exact state that you left it. So you can't take libraries that are designed for volatile memory. You can't take hash tables and B trees and key value stores that were designed for volatile memory and just use them on persistent memory and have them be consistent after a crash. They won't be consistent after a crash. So we need a way to add transactional updates to make them consistent. Most C programmers don't want to write their own hash tables. They don't want to write their own trees and so on. They want to use containers. They want to use things like the standard template library in C++. So that's the third requirement that came up again and again. It would be nice if we had nice, performant, validated ways of doing things like lists and queues and tables that you could just use. And then finally, it's easy to create errors in these algorithms. If you're trying to make an algorithm that makes a data structure stay consistent across reboots, it's easy to have bugs. So we need tools to help find those bugs. So that's kind of the last requirement. So we tried a few things in the beginning. The first thing that everybody comes up with is says, well, I'm a C programmer. If I use malloc to get memory, I just need a PMDK to get persistent memory. No problem, right? Well, of course, what happens if you call PMDK and you haven't linked that new memory into anything in your program crashes? So that's a memory leak. But it's worse than a memory leak because this is persistent, so it's a persistent memory leak. No one will ever clean it up. So that's not good. So instead, we tried this other thing. This is in the Linux example tree that I mentioned earlier. A little library called PMDK, and it breaks malloc into multiple steps. There's a reserve step, and then there's a step that says, okay, I'm ready to activate it, and the activate happens atomically. So this was kind of eye-opening for us. This was the first way where we found some really useful ways of managing persistence. But we realized that this was also kind of simplistic, and we could do a lot better than this. So we started looking at building PMDK at that point. And our goals for PMDK, again, were to take the things that we had heard of, the goals that we were asked, the requirements, and make a library that's validated and tuned for performance. Okay? Later we realized we had to add some more goals as these came up. We had to handle some of the harder stuff around RAS, reliability, availability, and serviceability. For example, what happens if there's a bad block? If there's a bad block in memory, like an uncorrectable block in your DRAM, your program will get killed. Sometimes the system even crashes. But the system will recover from that. It'll sequester that memory and you won't use it again. With persistent memory, it means you've lost some persistent data, so we need to handle that. That's a hard problem to solve. Okay, so the result of all this, leading up to it, was the PMDK set of libraries. It's a menu of libraries. PMDK is not one library. It's more like 11 or 12 libraries now. And you just pull in what you need. So in that programming model that I talked about before, here's the picture of where PMDK lives. Right? In the programming model, you can map persistent memory directly into your application, and you're free to just access it directly all you want. Or you're free to use the PMDK libraries to help you do that. But these libraries, they don't interpose storage interfaces. They don't interpose buffer-based interfaces to persistent memory. They allow you direct access to your persistent memory, and then they help you do things like start and end transactions. So it's quite different from any storage library that you've ever seen. They're designed for persistent memory from the beginning. As I said before, these are fully validated, they're performance tuned, and we have some tools for the developers that help find problems. I've got a slide coming up that shows you the tools. But most importantly, they're open source, they're product neutral, they're meant to work on multiple products across different vendors, even different CPUs. We do have code in our repository today for multiple operating systems. These run on Windows and Linux. We have code for ARM that we got from the ARM community. But of course, most of the team works for Intel, and so we spend most of our time tuning this to make sure that it's going to work on the Intel product. The core library there's roughly 10 in the core library, and we have some other libraries that are built on top of it. Over the period of about 5 years, we have about 8,000 commits. So compared to something like SPDK, that's not a lot, but on the other hand, it is a lot for a new library. We have a lot of users that we know about. We have some that we can't talk about because they're under NDA. They told us what they're doing under NDA. But we have a lot who do use it, and they're public about it. Some of them are giving talks in this summit, so you'll hear more about it. We have a lot of people doing it with open source, but closed source as well. The whole idea behind PMDK is let's make programming easier. We don't care if you steal the code and put it in your closed source product. We don't care if you rip the code apart and just steal snippets of code. The idea is to make programming easier. We're not trying to make money from PMDK, right? There's no charge. The most interesting library where the focus of all the work has been is called libpmobj. This is the most general purpose library we have. It has arbitrarily sized transactions, it has allocation, it actually has a lot of features, maybe too many features in fact. It's pretty featureful. Our team also took over maintenance of this library called libmemkind, which is for the volatile use of persistent memory. And it's been getting a lot of use lately in these volatile use cases. Just to show you what goes into these libraries. So we started the PMDK project about 5 years ago, and then about 3 years ago, we really got it to the point where we thought it was stable, it was well validated, and we pushed it upstream into a lot of Linux distros and started the Windows port. So this, it's hard to see at the bottom here, but this is the area for 1.0. So if you look at that performance, the performance of a B tree built using our library, libpmobj, we've got a benchmark, and we just arbitrarily, let's call that 100% performance. You can see with each version of libpmobj over the years, this is about over 3 years, that we've improved that B tree performance pretty significantly. We had a couple setbacks, but this is a really important point. The API was stable. The API hasn't changed. So if you use libpmobj, or an ISV uses libpmobj, with no work, they get the benefit of this performance increase, right? This is the reason to have a library. We're spending the resources to improve the performance of persistent memory. And if you use the API, you benefit, right? You get the 550% improvement on these APIs. This is all about getting rid of extra cache flushes, combining operations together, using the right instruction on Intel, and so on. We've really taken a lot of pain to try and continue to tune the libraries, and that's why we have a library. We have a library so that everybody benefits from the performance work and from the validation. So once we have these libraries, most of them written in C at the beginning, we start putting language bindings on them. We have Java support, we have C++ support, and the C++ support has been particularly interesting to people, so much so that you'll see talks in this summit about using C++. And I think those are some of the most interesting talks. We have a key value store called the PMDK for people who just want to use persistent memory with a nice, clean, and fairly easy to use API. There's a session on the PMDK coming up later today. I highly recommend it. And then we have other volatile use cases. Our latest library that was just added to PMDK is libvim cache, which is a volatile cache used for Spark. You're going to hear more about the tools in a minute, like things like vTune, because vTune has grown to support persistent memory. But we also have some other tools that you'll hear about in the talks today. All right, so where are we going in the future? So we don't think we're done. We don't think that we're done at all with PMDK. It's production ready. We have people literally shipping products using PMDK today. So it is production quality. But persistent memory is new, right? It's something that people are just learning how to use. They're learning how to leverage it. They're learning how to really get the value out of persistent memory. So every time we hear about a new use case, every time we hear about something we didn't think of before, we ask ourselves, what should we do with PMDK? What should we add? So we would love to hear from you guys and any user community. If you see problems with PMDK or if you see omissions from PMDK, let us know. We have lots of ways for you to help us. There's an issues database, there's a mailing list, there's a chat channel on IRC. Just let us know. And we will put energy into it because we want to keep the community engaged on it. So far, most of the pull requests, most of the changes have been made by Intel because we're the first ones to work on the library. We have some outside contributions, but it's nothing like what SPDK does. Like what Jim was talking about, SPDK has a huge community now contributing to SPDK. That's our goal. We want to be more SPDK. And so we're going to continue to enhance and refine what we have here. For example, in C++, we have a few containers that are working nicely. They're performant. They work for persistent memory. But the standard template library in C++ has dozens of containers. So we still have a lot more that we can add to be most useful. And we do get requests for other languages. For example, we get the request for Go. We get the request for JavaScript. So we have JavaScript bindings for the PMDK coming soon. We even get the request for Fortran, right? So if you don't see your favorite language supported, as long as it's not Fortran, let us know. Okay, so that is my summary of where persistent memory and PMDK is. Thanks very much.